Okay. So electrochemical cells are portable sources of electricity, and the electricity is produced from a spontaneous redox reaction. They call electrochemical cells voltaic cells and galvanic cells. Okay, it's the most common application of a redox reaction. To give you an overview of a standard electrochemical cell, there are two compartments. They call them half cells. One of them is where oxidation occurs. The other one is where reduction occurs. Oxidation is the loss of electrons, so it makes sense that this right here is an electrode. Typically, it's a piece of metal. In this case, it's a piece of magnesium metal, okay? And there's a wire that's connecting that magnesium metal to the other electrode, okay, which is copper. You've got electrons traveling from the magnesium metal towards the copper metal. This is based upon their location on the SRP table. Oxidation, loss of electrons, that's why it's flowing up here and to the right, and then reduction is gain of electrons. So that's why it's going to the copper metal, okay? Then you've got these solutions in which your electrodes are sitting. Those solutions typically contain ions of the metals or the electrodes, and then you have a salt bridge connecting. The salt bridge is used to help maintain charge, okay? In terms of how they may write stuff like this out in a problem, okay? If you're given two half cells in a problem, they may specifically write them this way, where they give you one metal and then they have this line, and then they give you the other metal ion half cell. So like this may be read for over here as an Mg line Mg plus 2 half cell, okay? This one would be a Cu line Cu plus 2 half cell, okay? And then in terms of the rest, anytime they're talking about standard cells, the concentrations of ions would be 1 molar and the temperature would be 25 degrees Celsius. Okay? And I think that's all we need to highlight on that page. Let's go to the next page. On the next page, they label, or they give you the definitions for anode and cathode. They did label the anode and the cathode here. Okay? So the anode is where oxidation occurs. The cathode is where reduction occurs. Okay. Now, on the next page, they also tell us about where we may have plating. So let's look at that. Okay. So here we've got copper 2 ions that are being reduced. So that means they're gaining electrons, and when they gain electrons, they turn into copper metal. So when they turn into copper metal, this is happening at the cathode. Plating means you are accumulating that solid metal on that electrode, okay? So that means that electrode will gain mass. So here it says the cathode increases in mass. That means that the other electrode, the anode, decreases in mass because the metal atoms are giving electrons away, which makes them turn into ions. So now those ions are filling the solution and we're losing mass. Okay? All right. I think that's all I need to highlight there. Let's take a look at the salt bridge. Let's come down here. If you didn't have a salt bridge, you couldn't maintain charge. So here it says that a salt bridge allows ions to migrate to complete the circuit. So ion migration counterbalances electrons flowing. So if you didn't have ions migrating through the salt bridge, like here you can see you've got nitrate ions migrating to the left and ammonium ions migrating towards the right. Okay, so if you've got these electrons coming here, you need this counterbalance to maintain the charge. If this didn't happen, there would be a charge buildup, and the reduction half cell would become negative, and the oxidation half cell would become positive, and then electrons would no longer flow. So that's why you absolutely have to have a salt bridge. Typically what they do is they take like a piece of a really small piece of like rope maybe, and they dip it in a salt solution and they hang it over the sides, and that's your salt bridge. Okay, I think that's all we need. This. Anions migrate towards the anode, cations migrate towards the cathode. Done. Go to the next page. Okay, sometimes they're going to give you an unusual electrode. I'm going to let you read about that. Okay, so read this briefly, and then let's take a look at the quick check. Why don't you do the quick check with the person sitting next to you? So you guys have got two half cells. You've got this chromium and silver. So you want to locate those on the SRP table and look for the one that's at the bottom right and the one that's at the top left. Okay, so the one that's at the bottom right is the chromium. Okay, so therefore it will be giving electrons to silver. So that's why the electrons are moving to the left. So that means that the electrode that is the anode would be the chromium metal. Okay? Yeah.
Does it matter that AG is also on the right in the table?
So AG with AG plus 1?
Oh, okay. So you do like...
Yeah. And then in which direction does the electron flow? They're flowing from right to left. And then in which direction do the cations flow? Through the salt bridge. So it says that the anions migrate towards the anode and the cations migrate towards the cathode. So that means they're going in the same direction, right? Because this is the cathode. So through here, the cations go to the left. And then plating occurs at the cathode. So that means the electrode that gains mass would be the silver electrode. We okay? Turn to the next page when you're ready. Yeah?
You're figuring out which is the anode and which is the cathode. What are you comparing? Are you comparing the ions in solution or the... Because they're both on the same side, right?
You have silver solid and a silver ion, and chromium solid and Cr plus 3. So down at the bottom, you tend to have solid metals. Do you see the chromium solid down there, like not even a quarter of the way up? Yeah. With Cr plus 3?
Yeah.
Okay, and then your silver is like...
No, it's a good look. It's below the overhead actually. Okay.
Like more, like a third of the way down from the top. So those are the, so then you are using, because this is a silver ion right here. So that is the one that's at the top left. Right here. This is on the bottom right. You don't want to use the silver with the sulfur, which is towards the bottom.
So for like this one, you would be looking at the left side for the silver, and then the right side for the.
Well, whichever one, you have a pair here. You have this, and you have this. You want to locate the pairs. So this one, since it's at the bottom, this one would be giving the electrons to this one.
Okay.
Okay, and then you would just write it accordingly. You would have to write, if you were writing this as a half reaction, it's the silver ion plus the electrons going to the silver metal. And then you would reverse the half reaction of the other one.
Okay.
Okay.
Thank you.
Okay. So on the next page, couple of things. The voltage that you generate with these batteries are called a potential difference because it measures the difference in potential energy between the 2 points. And then I'll show you what that looks like in a second. If you multiply a half reaction by an integer to balance the electrons, the cell potential doesn't change. And then tripling a half reaction does not affect the half cell potential since the energy per electron doesn't change. Changing the size of metal electrodes also does not affect the cell voltage. I have seen questions like this in the multiple choice portion and sometimes the free response portion. Okay, let's take a look underneath the sample problem. If you have a positive voltage, then that means the reaction is spontaneous. So that means a negative one would be non-spontaneous. If for some reason you get a negative voltage, you probably messed up on the half reactions. And let's take a look at the next page. So in practice problem number 1 on the next page, here they give you nickel and bromine. So what you do is you look at where they are on the period or on the SRP table. This is on the lower right. This one is up above there, so upper left. So that means we're going to take the Br2 plus 2 electrons. We're taking that half reaction. We're writing it as it is. And here they want us to calculate the standard cell potential. That means you need to write the voltage down. This is positive 26 volts. Okay. And then the other one, we have to reverse the order of the nickel. So this is nickel solid going to nickel ions and then 2 electrons. And then this potential is positive 1.09. Okay, now, when you add these together, obviously the electrons cancel. You also add together the voltages, and you're going to get positive 1.35 volts. Since it's positive, that means this is a spontaneous reaction, and we're good to go. Okay? Do you want to try one on your own, or you understand? Okay, let's talk about non-standard conditions. So underneath here, for non-standard conditions, that means you're not at 1 molarity and you're not at 25 degrees Celsius. So I'm going to let you read this. Go to the next page. So read non-standard, read cell equilibrium. The one thing in cell equilibrium right here that I would highlight of reactions, E indicates the same thing as KEQ. And there's an equation called the Nernst equation that converts E into KEQs. So you could have a really small voltage, but that means you could have a huge equilibrium constant. So read through this, and then underneath the Nernst equation, down here, I'm not going to go through the derivation. It goes on to the next page, right here. This is the final form of the Nernst equation. And the N that's right here is the moles of electrons transferred. So if you transferred 2 electrons, you would put that there. If you are at equilibrium, then you would be using this right here. Okay. And then the Danieli cell. Don't really need to talk about that. Turn to the next page. Take a look at the practice problems. Practice problem number 1 is where they apply the Nernst equation.